Okay, so we are going to solve a system of equations by graphing. Okay, so if you remember with what we have done so far, we have determined if it's one solution, no solutions, or infinitely many solutions. So what we are going to be doing is we are going to be graphing and actually looking for that ordered pair that is a solution. We're actually showing the graph of a line on top of another line, which means, with parallel lines, which would show no solutions. So we are going to be actually graphing the lines. And then finally, if you have a line on top of itself, or two lines on top of each other, then that would be infinitely many. So we'll start with example 1. I do have graph paper here. A couple things you need to know about solving by graphing. First of all, it's very inaccurate. So even like the thickness of your pencil, the copy of your paper and how big your graphs are, that all plays into account the accuracy of graphing. So you want to make sure that you are always using a straight edge and a sharp pencil. So if we look at the first system, let's go ahead and do y equals x plus 1 and y equals negative x plus 3. Remember, to graph a line, we are looking for the slope, which is m, and then the y-intercept. So we start with the y-intercept. So 0, 1. And then from there, we're going to use our slope of 1, which is the coefficient or the number in front of the x. So up 1 to the right 1. Up 1 to the right 1, up 1 to the right 1. I can do this. The more times I do it, the better off I'm going to be, the more accurate my line is going to be when I actually lay my straight edge down to draw it. And I am going to use a pencil to draw it. Make sure you're going through the points and you're actually going through the intersections. It doesn't take much to throw it off a little bit. Okay, so there's one line. Looking at the second one, I have a y-intercept of 3 and a slope of, remember, negative 1. So down 1 to the right 1. Now notice I already found where they have the points in common because I just landed on that line that I just drew. Down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. Use my straight edge again to draw the line. And looking for the one point that they have in common. And that would be right there. Remember, do not confuse this with slope. This is a point. So to the right, 1, and up 2. So what we're saying is that this ordered pair will work in both of these equations. So let's check that real quick. I have my y. This is my check. My y is 2 equals x, which is 1, plus the 1 that is already there. I end up with 2 equals 2. It checks. But I gotta check both of them. If I put a 2 in for y equals negative 1 times my x, which is 1, plus 3. 2 equals negative 1 plus 3, and I'm back to 2 equals 2. It also checks. It has to, this ordered pair has to work in both of them to truly be a solution. Do another one. Make this example 2. I'm going to pick a little bit harder one. So 2x plus 5y equals 9, and 3x minus 5y equals 1. The reason why I'm writing these particular two side by side is because I notice that this is not in slope-intercept form. So I'm going to have to do some algebra to actually get it in slope-intercept form. So I'm solving for the y. That means I'm going to subtract 2x on both sides. So 5y equals, I'm going to change markers here. So 5y equals, get in the habit of putting that x term first, negative 2x plus 9, and then divide every term by 5 to get y by itself. Now that y-intercept is nasty, so we'll see how this graph actually comes out. 3x minus 5y, I need to put this in slope-intercept form as well. I'm going to subtract 3x from both sides and have negative 5y, don't forget that negative, equals negative 3x plus 1. Divide every term by a negative 5. And I have y equals a positive 3/5 x minus 1/5. Now this is going to be a nasty one to graph. Just because I have fractions does not mean that I'm not going to get a nice, neat ordered pair. I would never be so cruel as to have your solution, if it's a graphing problem, end up being some weird decimal. Okay, I'm going to get a clean sheet of graph paper here. So my y-intercept is 1 4/5. So 1. Actually, I think I'm going to blow this up a little bit. Oopsie, wrong way. So you can see a little bit easier. So 1 4/5, well that's not quite 2. We'll see how that works out. So there's that. With a slope of negative 2/5, so that means down 2 to the right 5. I'm going to go down 2 and to the right 5. 1, 2, 3, 4, and 5. So you should not be on a line because this isn't on a line. I'm going to go down 2 again. 1, 2, 1, 2, 3, 4, and 5. This may be really bad. We'll see how this turns out. Okay. I'm going to graph my second line. So y-intercept of negative 1/5. It's just a little bit, so it's like right there, with a slope of 3/5. So up 3, 1, 2, 3, and then to the right 5. 1, 2, 3, 4, and 5. Do that again. Up 3, 1, 2, 3, and to the right 5. Okay, so I'm going to very carefully graph. Okay, now I'm going to blow this up really big. Now, notice I did not intersect exactly, pretty dang close. So I think that my ordered pair, or my solution, is the ordered pair of 2 and 1. I think it is. I need to check that. So I'm going to go back and plug it in to my original equations up here. I'm going to go back to the originals, put a 2 in for x. So 2 times 2 plus 5 times my y equals 9. 4 plus 5 equals 9. So 9 equals 9. So that worked. Let's try my other one. 3 times my x of 2 minus 5 times my y of 1 should equal 1. 6 minus 5 equals 1, and 1 equals 1. So it does work in both. So again, proof being that just because you end up with really nasty slope-intercept forms and nasty y-intercepts, that does not mean that you're not going to get a nice, neat number for an ordered pair. And then also remember that if you end up graphing, just a quick, you end up graphing a line and you have another line that ends up being graphed parallel to it. So you have to look at the same slope. So this would be no solutions. Or if you graph a line, let's zip through this way. You graph a line and you end up graphing another one right on top of it, then those will have infinitely many solutions.